minute?
It's okay, yeah.
Okay, let's see, I think I'm almost ready. Let's see, are you seeing the slides?
We got them.
Okay, good. Well, hello again. Happy to be here again talking about section T7 mostly in the Technician Management Guide. And again, I'm Randy, KJ7WLT, and please feel free to interrupt with questions as we go along or type questions into the chat and we'll come back and deal with them later, or I'll deal with them when I see them. This particular set of questions, there's 4 different groups of questions, and I think on the actual exam, there's only 1 question from each group, but there's about 11 questions in each group that are in the manual that have discussion and the answers in the manual. And so I'm going to go through these again. As last week, I'm not going to go through them exactly in the same order that they're listed in the book or lists of questions, because I think some of them fit together better in different orders. Let's see, is there a problem with my audio or visual? I see someone waving there. Is there a problem?
Coming through loud and clear for me.
Okay. Well, let me know if there's any problem, or send a note in the chat that we can deal with. Yeah, so I'm going to kind of bounce around a little bit between different topics in here. Again, the whole question pool you can get from the ARRL website, and I've also borrowed a number of figures from this AD7FO site, which has answers to all the questions as well. And again, there's lots of online tools for practicing these exams. One I particularly like is the hamstudy.org, but there's others out there as well. So I'm going to kind of dive in, but please, again, feel free to interrupt with questions as we go along. And this first one, if you were here last week, this kind of relates to something that we talked about a lot last week. What is the name of a circuit that generates a signal that oscillates at a specific frequency? Well, I kind of gave it away there. I said it oscillates at a specific frequency, and the answer is it's an oscillator. And remember, last week we talked about these tuned circuits that can be created with an inductor, this symbol that looks like a coil of wire, and a capacitor, which is like 2 conducting plates with a non-conductor in between. And if you hook these up properly, then you can get a sort of oscillator where the current goes back and forth, back and forth, back and forth, kind of like a pendulum swinging. And it creates a signal that oscillates at some particular frequency. And by adjusting the inductance, for example, you can very finely tune what frequency it's oscillating at, and it's used both for producing radio waves and also for filtering particular frequencies when you're receiving waves. Okay, so there's some basic questions here about equipment. What is a transceiver? It's a combination, as the name suggests, it's a combination of a transmitter and a receiver. So anything that both transmits and receives is a transceiver. So the AM radio in your car is not a transceiver, it only receives, but any ham radio would typically, or at least many of them, combine the transmitter and the receiver into a single unit, whether it's a handheld, a mobile radio, a big desktop radio, or even your iPhone, for example, is a transceiver because you can both talk and listen to other people when you're making a phone call. What's the function of a transceiver's PTT input? Well, if you remember what PTT stands for, it's typically written as push to talk, but you can also think of it as push to transmit. When you push down on that button, then what you say, it gets transmitted. And so it's what switches the transceiver from the receive mode that it's normally in when you're just listening to the transmit mode when you actually want to say something, you push the PTT button. Which of the following describes combining speech with an RF carrier signal? So RF is radio frequency. So we've got a radio wave that's being sent out at some frequency by your transmitter, but it has to, or you typically want it to include some interesting information like your voice if you're talking into your radio. And so you can't just send out a tone at a single frequency. You typically have to modulate it somehow. And modulation is what we call it when we take a pure frequency and somehow change it so that it includes some information. So you can, for example, modulate the amplitude, make the signal louder and softer. That's called amplitude modulation, or AM radio. Or if you modulate the frequency, just change the frequency a little bit from the baseline frequency that you're transmitting on, then that's frequency modulation, or FM. But modulation is any way of combining speech with the radio signal. Which term describes the ability of a receiver to detect the presence of a signal? So if you can detect it at all, you have to be fairly sensitive to that particular frequency. And so sensitivity is the ability to detect the presence of a signal. So this is question T7A1, but then T7A4 is a very similar question. Which term describes the ability of the receiver to discriminate between multiple signals? So you may detect several different signals, but you want to pick out one of them that you're trying to listen to, one particular frequency, and ignore all the radio waves on other frequencies. So that's somewhat different from sensitivity. That's selectivity, being able to select which frequency you want to listen to out of all the ones that are hitting your antenna. So selectivity is the ability to discriminate or select between different signals. So what's the function of an SSB/CW-FM switch on a VHF power amplifier? So there are a lot of acronyms there, but if you remember what these stand for, SSB is single sideband. That's one form of modulation. CW is Morse code, and for continuous wave, that's another way of encoding information in the radio wave signal. Or frequency modulation, which I mentioned before, is another way or another mode of encoding information. So all of these are different modes, we call it, of encoding information in the radio signal. And so the switch that changes between SSB and CW or FM would be something that is choosing what mode you want to use. So the correct answer is the one that talks about selecting a mode. And just remember that these are different modes that you might want to select depending on what kind of way you're trying to encode your information. Okay, so what device increases the transmitted output power from a transceiver? So if you're trying to increase the power, then you want to use an amplifier. So to increase the power is the same as to amplify the power. And in this case, the power output is in the form of radio waves at radio frequencies. So that's what the RF stands for here. So an RF power amplifier is amplifying or increasing the power of the radio waves that you're generating. Where is an RF preamplifier installed? So a preamplifier is like an amplifier, but pre sort of gives us a hint that it's doing something before it reaches the main device. And so the answer is that it's between the antenna and the receiver. So it takes the signal that's coming in from your antenna, and before passing it into your receiver, which tries to amplify the signal itself, it's doing some additional pre-amplification. So before sending it to the receiver, it amplifies it a little bit more and can increase your ability to hear weak signals, for example. So the radio frequency preamplifier is before the receiver, which has its own amplifier. Which of the following is used to convert a signal from one frequency to another? Here the answer is a mixer, and it's not quite clear. It's a little hard to explain exactly why it's called a mixer, but the idea is that a mixer takes two different frequencies as input and then outputs signals that are at two new frequencies that are the sum and the difference of the input frequencies. So we're not going to get into the physics or mathematics of how that works. You just have to remember that converting from one frequency to another requires a mixer. And you can eliminate a lot of these others, like an amplifier we know doesn't convert from one frequency to another. It just amplifies what's coming in on the desired frequency.
Randy, you got a hand up?
Oh, I'm sorry, there's a hand up, yes. Was there a question?
Not sure who it is. It says Galaxy S21 5G.
Maybe the hand's up by accident, but if you have a question, feel free to ask it or type something in the chat. Okay, I'll go on for now, but feel
Okay.
free to interrupt. Yeah, so that's a mixer. And then what kind of device converts the radio frequency input and output of a transceiver to another band? So this is also sort of converting radio frequencies from one band, one set of frequencies to another. And the answer here is a transverter. And again, you just have to remember what this is called, but you can eliminate some of these other things because it's not a filter of any sort that is sort of filtering out high frequencies or filtering out low frequencies. If you're converting it from one band to another, then convert sounds kind of like transvert, and they mean roughly the same things. So that's one way to remember perhaps that it's transverter, and it's not the one that has converter in the name, even though it's converting, but it's not converting the phase, which is sort of the how the peaks and valleys of the wave are organized, but it's converting it from one band to another band. So it's a transverter. Okay, those I think were all the questions in the section T7A. So maybe before we go on to the next section, I should stop here and see again if there are any questions or any confusions about these questions. Okay, so let's go on to the T7B questions. Again, I'll kind of mix them up between sections a little later too, but most of the next few are from the T7B section. And a lot of these talk about what you can do if you're having problems sending or receiving signals. So if you're told that your FM handheld, your little HT handheld ham radio, or your mobile transceiver is over deviating, what does that mean? Well, it typically means that you're getting too much sound into the microphone, and what you need to do is move the microphone farther away from your mouth. So over deviating means too much of something. It's too much amplitude in this case, and so you want to move it away, move the microphone away from you, not talk louder into it. That would be the wrong thing to do. What might the problem be if you receive a report that your audio signal through an FM repeater is distorted or unintelligible? So if somebody else on the repeater says, I'm having a really hard time understanding your signal, what could the problem be of these? Your transmitter is slightly off frequency, or your batteries are running low, or you're in a bad location? Well, it could be any of those, right? All of those are possible reasons why your radio signal isn't reaching the repeater very well. If you've got it set to the wrong frequency, or there's something wrong with your radio and it's transmitting at slightly the wrong frequency, then it's not going to be picked up very well. If your batteries start getting low, then it may not be transmitting at full power. Or if you're in a bad location, sometimes just moving a few feet one way or another on the UHF and VHF frequencies that repeaters use can make a big difference. What's a symptom of radio frequency feedback in a transmitter or a transceiver? Well, if you're getting feedback, that means that the radio signal you're trying to send out is getting some noise coming back that's distorting or making garbled the transmission that you're trying to make. So you can think of the feedback as sort of mixing the new signal with the feedback, and it's creating something that's garbled. And so you might get reports that your audio sounds garbled or distorted or unintelligible. So any of these are the sort of thing that someone listening to you might report if you're getting feedback. Which of the following actions should you take if a neighbor tells you that your station's transmissions are interfering with their radio or TV reception? So if they come knock on your door and say, I'm getting lousy reception on my radio or my TV, and I'm sure it's your ham radio that's to blame, what should you do, or what's the first thing you should do out of these choices? Well, the first thing to do is always make sure it really is your radio that's the problem. And a good way to test that is to turn on your own radio or television and then transmit on your ham radio the way you were when you got this complaint, and see if that's causing any problems on your own radio or television. If your own radio and TV are in the same house as your ham radio, then they're probably going to suffer the same problems your neighbor is if it's really your radio that's to blame. And so before doing any of these other things, the first thing you should do is try to determine whether it really is your ham radio that's causing the problem. And at any rate, you probably don't want to contact the FCC, the Federal Communications Commission. They're not going to deal with this sort of problem directly anyway, unless your neighbor complains to them. Turning it around a bit, what would you do, or what should you do if you think something in your neighbor's house is causing harmful interference with your amateur station? So if you're having a very hard time hearing anything on your radio, you're getting lots of noise and static, and you're sure it's your neighbor's device of some sort that they're running that's creating all sorts of radio frequency noise that's interfering with your ability to use your ham radio, what should you do? So here's some choices. You could work with your neighbor to identify the offending device. Go knock on their door, politely ask them to help you sort out the problem. Actually, let me just tell you, all of these choices are correct. You should do all of these things. You should be polite to your neighbor and try to work with them, but also inform your neighbor, if you have to, that the FCC rules prohibit the use of devices that cause interference. So if you can identify that it's one of their devices that's causing a lot of interference and noise on a ham radio frequency, and it's interfering with your ability to communicate, then that's against the FCC rules, and there's laws that cover that. And so that gives your neighbor hopefully some incentive to work with you rather than having you go and report them to the FCC. And then you should also make sure your own station meets the standards of good amateur practice, so that you're not doing anything wrong that might be interfering with your own ham radio experience, and that it really is the problem really is coming from your neighbor and not from yourself. So all of these choices are correct. So what would cause a broadcast AM or FM radio to receive an amateur radio transmission unintentionally? So let's unpack what that means. So a broadcast AM or FM radio. So broadcast radio means radio like a radio station that you tune to in your car or on a transistor radio. It's a radio station that's broadcasting to the whole world, or at least whoever can reach their signals. So it's a commercial station or a public radio or something like that. It's not ham radio. So a broadcast AM or FM radio, if you have a broadcast AM or FM radio, like the one on the dashboard of your car, built into your car, or a little transistor radio, if it's receiving an amateur radio transmission unintentionally, what's the problem with that? And the answer here is A, the receiver is unable to reject strong signals outside the AM or FM band. So if you've got an AM or FM radio that's only supposed to be picking up the broadcast frequencies for AM and FM radio, then it should be automatically rejecting frequencies that are outside of those bands, and it shouldn't be picking up ham radio frequencies, or at least it shouldn't be amplifying them and sending them to the speakers, so you shouldn't be hearing them. So maybe it's a problem with your radio. You should have your radio checked out if you're unintentionally receiving ham radio transmissions on it. Or if your neighbor complains that they are, then you might want to suggest that they have their radio checked out. Which of the following can reduce overload of a VHF transceiver by a nearby commercial FM station? So here they call it a commercial FM station. I think it's the same as what they meant by a broadcast FM station on the previous slide. They just mean a station that's broadcasting radio to the community. And in this case, the answer is you could install a band reject filter. So here they're talking about if you have a VHF transceiver. So by VHF transceiver, they mean a ham radio, an amateur radio, and that's operating in the VHF band, which is, the 144 to 148 megahertz sort of band that handheld radios operate on, for example. If that's being overloaded by a nearby commercial FM station, that means there's some commercial station or public radio or somebody who's broadcasting such a strong signal that your ham radio is picking it up and it's interfering with your ability to hear the ham stations. Then well, you might want to have your radio checked out to see if there's a problem with it, but you can also put a little device in between the antenna and the radio that does a better job of excluding other frequencies, and that really filters out all the frequencies that aren't in the ham radio bands and that shouldn't be coming into your radio or shouldn't be amplified by your radio at all. So a band is a range of frequencies, and a band reject filter would say certain ranges of frequencies should be rejected as it comes in through the antenna before it even goes out to your radio, so that it doesn't interfere with the ham radio bands, the frequencies that you're trying to listen to. And what should be the first step to resolve non-fiber optic cable TV interference caused by your amateur radio transmission? So again, there's a lot of words there, and I think the answer is to be sure all the TV feed line coax connections are properly installed would be the first thing. And it's always good to just remember, and as a hint for this particular question, that if you're having problems with any of your electronics, the first thing to do is always to check that the connections are right and that something's not unplugged or loose someplace. And here the other answers they've added are to distract you from that correct answer. But I think going back to the question, the fact that they say it's a non-fiber optic cable TV, I think that's just to sort of imply it's a TV with a coax cable connection that has radio waves or waves like radio waves traveling on it, and that therefore it might be interfering with amateur radio. I think that an optic cable, the way optic cables work, there's actually light that's being passed up and down the cable, and so it's less likely to interfere at all with an amateur radio. So that's, I think, the only reason they put that non-fiber optic cable bit in there. But again, for this question, just remember the first step, if you're having problems like this, is just check all the feed lines. Which of the following can cause radio frequency interference? And in this case, all of these choices are correct. Fundamental overload just means that you're getting a very strong signal at some other frequency that's kind of interfering with the frequency you're trying to listen to. Harmonics means signals that are at different frequencies. And if you're a musician or know about music, you're familiar with harmonics of musical notes that are basically notes that are at like twice the frequency or 4 times the frequency, that are up an octave or 2 octaves on the piano, say. Those are called the harmonics. And also with radio waves, if you have an antenna that works at 1 frequency, it also often works very well at harmonics of that, at twice the frequency or 4 times the frequency. And so if there's a noise that's coming in or a strong signal at one of those harmonics, then your antenna might be picking that up quite well as in addition to the frequency you're trying to listen to. So that can cause some interference. Spurious emissions. Emission refers to, generating radio waves that are generated, and spurious just means sort of wrong emissions that shouldn't be generated, but that are generated due to some problem in the equipment, for example. So any of these could be causes of radio frequency interference that you might hear.
Randy,
Yeah.
I'd like to comment on your hint.
Yes.
If you're using an antenna that you want to use a harmonic frequency on, it's multiples of 3.
Ah, interesting.
So if you're on like the 15 meter band, well, the harmonic of that is or actually the harmonic of the 40 meter band is the 15 meter band. So you can use the 40 meter antenna will have a triple of the 15 meter frequency.
Right. And also the UHF bands are at like 75 centimeters, and the 2 meter band, the VHF frequencies are at 2 meters, and 2 meters is roughly 3 times 75 centimeters. Okay, yeah, I should update that slide. Thank you.
Okay.
Maybe I should pause here also and see if there are any other questions at this point. Okay. Which of the following could you use to cure distorted audio caused by RF current on the shield of a microphone cable? So since they're talking about RF current, radio frequency current on a cable of some sort, there's all sorts of cables that can generate RF frequencies that can be a problem. And the general solution is to use something called a ferrite choke, which is, ferrite means a piece of iron typically, and choke refers to the fact that it sort of filters out some of these frequencies that can be a problem if they're generated on cables. So you may have some cables like these USB cables shown here. You might have power cables on your laptop or on other equipment that sort of have a built-in ferrite choke. If you've ever wondered what these sort of round cylinders close to a power outlet on a cord is, for example, that's a ferrite choke. You can also buy ones that look like this that you can snap on to wires. You can get bigger ones that are rings of iron that you can wrap a cord through several times. But on all sorts of cables, on antennas, on power lines, on microphone cables, it's often a good idea to put a ferrite choke in to filter out some of the current that can move on the cable itself and create radio waves that can interfere with what you're trying to listen to. How can fundamental overload of a non-amateur radio or TV receiver by an amateur signal be reduced or eliminated? So again, they're talking about non-amateur radio or TV receivers, so just broadcast radio or TV. And what if that's being overloaded by an amateur radio, a ham radio signal? Well, one way is to block the amateur signal with a filter at the antenna input of the affected receiver. We talked about this kind of one of the other questions was a different aspect of this. If you're picking up broadcast FM radio on your ham radio, you can put a filter in that filters out the broadcast radio frequencies and only allows in the amateur radio signal. Here you can sort of do the opposite. You can put in a filter that filters out the amateur radio signal at the input of the TV receiver or the radio receiver. But one way to remember that this is the right answer is it's the only one that sort of talks about modifying the receiver. All the others talk about modifying the transmitter. And it's not really clear here whether they're talking about the transmitter of your amateur radio or the transmitter that's transmitting the non-amateur radio or TV signal, the broadcast station. But you certainly can't do anything to change those transmitters. So the best thing to do is to fix your own receiver. Okay, so I'm going to skip over the T7C part for the most part, come back to that in a minute, and jump to the T7D questions. But before doing that, let's see again, are there any questions on these? The set of T7B questions were largely about sort of filtering out noise and different kinds of distortion and different kinds of interference you can get and how you can deal with problems if you're getting interference on your amateur radio or causing interference with your neighbors. Okay, so the T7D questions relate a lot to different kinds of devices for measuring things. And the first question is, what instrument would you use to measure the electric potential? Ammeter, voltmeter, wave meter, ohm meter? Well, if you remember that electric potential is another way of talking about the voltage. The voltage difference between 2 points is called the potential, which is measured in volts. Then the device you use to measure that potential between 2 points is called a voltmeter. Ammeters and ohm meters we'll talk about also in a minute, but amps are the unit of electric currents. How many electrons are flowing past the point on a wire, for example, and ohms are the resistance that the wire has to the flow of electrons, whereas the voltage is the potential that's causing the electrons to move. So the difference in electric potential between the positive and negative ends of a battery is the electric potential or the voltage of that battery that can cause electrons to move through a wire if you attach a wire to the two ends of a battery. So suppose you want to measure the voltage, how would a voltmeter that's used to measure the voltage or the potential, how do you connect it to a circuit in order to measure the voltage? And there's a couple of questions like this. We'll also look at ammeters in a moment, but the two choices that make the most sense if you sort of study this material is it would be either in series or in parallel. And I'll remind you what those mean, but of those two, for measuring the voltage, you want to connect it in parallel. So this figure is supposed to indicate sort of how you would hook up a voltmeter. So these V1, V2, V3, V4 are all different positions where you might put your voltmeter and put the two connectors that come out of it on the wire, maybe on two different sides of a resistor or on two different sides of a battery here. But any of those places where you put the voltmeter, you basically take the two probes of your voltmeter. I meant to bring my multimeter up so I could show you, but it has, for example, two little probes on it, and you connect one to the positive pole on your battery, the other one to the negative pole to see how much voltage that battery has. Or you can connect them across a resistor, for example, to see what the change in potential is across that resistor that's forcing electrons to move through it. And the fact that it's in parallel means that when the electrons are actually flowing through the circuit, this circuit that goes from the wire up to the voltmeter and back is sort of parallel to the circuit that the electrons are actually flowing in. So you put it in parallel. By contrast, this little A device up here is an ammeter, which is in one of the future slides, and it's shown connected in series. So the ammeter, which measures the current flowing through this circuit, you actually have to put in the circuit in such a way that the current has to flow through it. The only way you can measure the current flowing through here is by putting the ammeter in series here. But the voltmeter, you can just touch the two probes to 2 points on the wire, and it will tell you the difference in potential between those 2 points, the voltage between those points. But before we get to the ammeter, there's some questions also about things called multimeters. So a multimeter is a device that combines several of these things: voltmeter, ammeter, ohm meter, typically. And in particular, a multimeter can measure both voltage and resistance. So it's both a voltmeter and an ohm meter. And multi means many different things. And so a multimeter can measure more than one thing. Typically, a multimeter combines a voltmeter and an ohmmeter, and also usually an ammeter for measuring current. But of these choices, C is the only one that's correct. So here's the other one about measuring current. If we want to measure current, and here it doesn't say an ammeter, which is what you would use to measure current. If you had just a single device, it says if we want to measure current with a multimeter, how would we combine that? So they haven't said they're measuring ohms. They haven't said it's an ohm meter, but since we're measuring current with a multimeter, we're using it as an ohm meter. And I showed you on that previous diagram that in this case, the ohm meter or the multimeter, if that's what you're using, has to be plugged in series here, meaning that there's a series from the battery to the ohm meter to whatever devices you have that have some resistance and back to the battery. It's all one series. It's not in parallel like these voltmeters are attached. And that, again, the reason is that in order to measure the current that's flowing through the wire, you really need the ammeter or the multimeter in the circuit so that the current that's flowing through these devices down here, the different resistances, also has to flow through this meter in order to measure the current. Okay, which instrument is used to measure electric current? Well, as we just saw in the last question, it could be a multimeter. But if you had just one device to measure current, then it would be the ammeter. And the ammeter measures amps, which is short for amperes, which is the unit of current that's used, which is named after a French physicist from the 19th century. So now that we know a bit about how a multimeter works and how voltmeters and ammeters are connected in different ways, which of the following do you think can damage a multimeter? Correct answer is C, attempting to measure voltage when using the resistance setting. So what that means is you've got a multimeter, but you've turned the dial so that it's trying to measure voltage. And if it's trying to measure voltage, it expects you to put the two probes in parallel with your device, like just touching the wire in two different points, but not having the current actually running through the wire. Sorry, let me start over. I'm saying this backwards. If you're in the resistance setting, then it's working as an ammeter. So it's expecting the current to have to go through the device in order to measure it. So when you have it set in the resistance setting and you connect the two probes to two different points on the wire, it allows the current to go through your meter in order to try to measure the current. But if you think you're trying to measure voltage, and that's why you've touched the wire in two different points, it may be that there's such a large current running through the wire that once it starts going through your multimeter, it destroys your multimeter in the process. So you don't want the current running through the multimeter if you're trying to measure a large voltage, for example. But if you have it set on the resistance setting, then it allows the current to go through the multimeter because it thinks you're trying to measure the current, and that can fry the device if what you hooked it up to has too large a voltage for the amp settings on your multimeter. I don't know if that was clear. Questions about that or anything else? Okay. What reading indicates that an ohm meter is connected across a large discharged capacitor? So here the answer is an increasing resistance with time. And so it's the idea here is that if you hook the ohm meter up and the capacitor is charging up, remember how a capacitor works, you get some flow of current into one plate of the capacitor and away from the other plate of the capacitor until it reaches some voltage potential across the capacitor, and then the current stops flowing. So as the current stops flowing, the current goes down. And so your ohm meter is trying to calculate resistance by calculating the voltage between 2 points and dividing by the current that's going through it. And remember the basic formulas for how resistance is related to voltage and current. So if the voltage stays the same, but the current decreases because the capacitor is charging up and now there's no more current flowing, then the resistance is going to be divided by smaller and smaller values. And so the resistance is going to appear to get larger and larger because the current is decreasing in this case. So that's a little complicated, but if you think about it and go back and review the formulas for resistance, voltage, and current, maybe that will make more sense. But in this case, the fact that it's an ohm meter tells us that we're trying to measure resistance, and ohms are a unit of resistance. So that allows you to immediately say it must be either A or B. Those are the only two that mention resistance, and that's what we're measuring with an ohm meter. And then you just have to remember one way or another that it's increasing resistance with time as the current decreases in this particular situation. Which of the following precautions should be taken when measuring the resistance with an ohm meter? So if you're hooking up an ohm meter to a circuit and you want to know how much resistance is there between one point and another, then the way your ohm meter or your multimeter tests that is by creating a little bit of voltage difference between the two probes that you're touching on either side of the device you're trying to measure the resistance of, and see how much current flows as a result. And again, it uses this formula from the last slide that the resistance is the voltage divided by the current. So it applies a little bit of voltage. Your meter creates a little bit of voltage. It can act like a battery sort of, and then it measures how much current flows as a result of that. And so the answer here is that you want to make sure the circuit is not powered, because if the circuit already has a large voltage on it, then that could destroy your multimeter. It could create a much larger current going through your multimeter than you want, because it's trying to measure a very small current by applying a very small voltage. But if there's already a very large current flowing through your circuit, then that's going to flow through your multimeter and destroy it if it's in the setting of an ohm meter to measure resistance. Okay, so I think that's most of the questions from the section T7D, and we only have one left and not too much more time, so I'll launch right into that. But again, if there are questions, we can talk about those at the end. So what's the primary purpose of a dummy load? So if you've heard this term, this is something related to antennas, and it's often used in place of an antenna on a radio in order to test your radio in ways where you don't want to actually be transmitting over the air, or in cases where you just want to make sure that if you accidentally press the push to talk button, you don't try to transmit over the air because you don't have an antenna hooked up. So for example, many hams, when they're not using their radios, will disconnect the antennas as protection against a possible lightning strike, for example. You should also have your station grounded if it's a big enough ham radio station, but often disconnecting. Somebody needs to mute, I think.
Lúc đấy thấy cuộc gọi nhưng mà tại đang nói chuyện với cái người bạn á, thế à. Thì không gắn cái điện thoại vào xe rồi nói.
Can somebody please mute? We're getting 1+ DE 2118. I think you need to mute. Okay, thank you. Yeah, so if you don't have your antenna hooked up and you want to make sure that you don't fry the radio when you press the push to talk button, which can generate a lot of energy that it tries to send out to the antenna, but if there's no antenna there, it may instead destroy the radio. When you take off your antenna, you can put on a dummy load, and this is a small one that just screws right into the antenna connection on your radio. This is a bigger, fancier one, but the basic idea, although the answer is here to prevent transmitting signals over the air when making tests, it's also a good idea just to to prevent accidentally trying to transmit signals when you don't have an antenna attached. And so rather than an antenna, the radio energy goes into this dummy load. So how do you make a dummy load, or how do they make dummy loads? What goes into a dummy load? And the answer here, it's a non-inductive resistor mounted on a heatsink. And so just remember that sort of the purpose of the dummy load is to absorb the radio energy. So a resistor is good at absorbing the energy, but it converts that energy into heat typically. And so you need a heat sink so that the dummy load doesn't heat up and burn you or get your radio too hot. So if you remember those two things, it's a resistor to absorb the energy and a heat sink to absorb the heat that's created by the resistor. That's what a dummy load is basically. Okay, which of the following is used to determine if an antenna is resonant at the desired operating frequency? So resonant typically means that waves of a particular frequency sort of bounce back and forth on your antenna. It's the right length related to the wavelength of the radio waves at the frequency you're trying to use. And you would like to sort of analyze your antenna to see whether it's operating right. And the answer, the answer is an antenna analyzer. This is just a picture of an antenna analyzer, for example. This is one that you can plug into an antenna, and then it shows a value of the SWR, which we'll talk more about in a moment, the standing wave ratio, which is a measure of how well the antenna is working at a particular frequency. And here it's set to some frequency, and SWR of 4 is very large, but the other end of this cable actually isn't attached to an antenna, so that's why the SWR is so bad in this case. But anyway, for this question, just remember that you're trying to analyze your antenna to determine what the SWR is, which is a measure of how well it works at a particular frequency. This particular one has a USB that you can plug into a laptop, so you can make nice plots of how the SWR varies with frequency, for example. Okay, now there's a set of questions on SWR meters and readings, and let's see, how much time do we have? I think we have enough time. I'm going to try to show you a few animations I made that I hope will kind of explain what SWR is, because it's kind of a funny concept. But the basic idea, let's see if I have, I think on one of the later slides, maybe I have a link to a web page where I put some of these animations, but I have them just on my laptop. So the idea of all of this is that we've got an antenna, a feed line coming out of your radio that's hooked up to an antenna. And in all of these figures, this dashed line represents the interface, the connection between the feed line on the left and the antenna on the right. And ideally, what happens is that you create a radio wave in your radio, and it propagates along the feed line, and it propagates into the antenna at exactly the same amplitude and frequency. And there's no reflection at this coupling where the feed line is connected to the antenna. And so this is kind of the ideal case, that these waves, which are propagating, and in the case of radio waves, the signals are oscillating millions of times per second and moving at the speed of light, more or less, but I've slowed everything way down here. But you've got this wave that's simply moving from the feed line to the antenna, and the amplitude that you're seeing on the antenna is the same as it was on the feed line. So that's what you would kind of hope to see. Now, in the worst possible case, though, you might have a bad connection between the feed line and the antenna that maybe doesn't let any of the energy pass through, and instead it all reflects back and goes back in towards your radio. That would be a bad situation, and that would look something like this, where the radio wave is moving to the right along the feed line, but it's not being transmitted at all into the antenna. Instead, there's this other wave that's moving in the other direction, the green wave that's moving back from the connection back towards your radio, okay? And that's very bad because all of that energy goes into your radio and might fry it. So you definitely don't want that situation. But what's shown down at the bottom is a sort of combination of these two, because what's really happening in the wire is there's the wave that's being sent to the antenna, and then there's this reflected wave, and they're both present on the wire at the same time. So if you really look at how the voltage or the current is varying on the wire as this wave propagates, as this wave propagates, if I can go back to the beginning here, as this wave propagates, what you see down below is the black curve is just the sum of the wave you're trying to transmit and the wave that's being reflected. And what you see is that that combination of the two looks like something called a standing wave, rather than looking like it's propagating to the right, traveling to the right, like our incident wave, or traveling to the left, like the reflected wave. Instead, it looks like things are just going up and down. And that's called a standing wave. And when you have perfect reflection of all of the energy and no transmission at all into your antenna, then if you really looked at how the voltages are varying in your wire, it would look like the standing wave. The combination of the two gives you something that looks like that. So that's kind of the worst possible case. Now, a real antenna is typically somewhere in between these two extremes. So the third video sort of shows the intermediate case where we've got some of the wave that's transmitted towards the antenna makes it through, but some of it is reflected. And here it looks like maybe about half of the amplitude of the wave goes onto the antenna, and the other half goes back and is reflected. And so if you look at the top two plots, you see the wave propagating towards the antenna, part of it being transmitted, but half of it being reflected back in the other direction. Okay, so we have the transmission down the wire onto the antenna, but then also this reflected wave. But now if you add together the wave that's moving towards the antenna and the wave that's being reflected back, and look at how does the voltage actually change at any particular point on the antenna, then the sum is this black curve down at the bottom. And what you see is it kind of pulses now. It looks like it's propagating from left to right, but its amplitude is getting larger and smaller and larger and smaller as it goes along. That's just kind of how the mathematics works out when you add these two signals together. And so what's shown in red here is what we call the envelope of that signal. It's kind of at each particular point in space, the voltage, if that's what we're looking at, never gets larger than this value at this particular point, but at other points it does get much larger, and then at this point it never gets larger than this, and here it gets larger, and so on. And so this SWR that is used to kind of measure how good your connection is between the cable or the radio and the antenna refers to this red curve at the bottom, this envelope of this sort of what's kind of like a standing wave and kind of like a propagating traveling wave. So the standing wave ratio refers to sort of the maximum value this red curve takes divided by the minimum value. So here, this value here is about 3 times as large as this value relative to 0 here. So it goes up to about 1.5 and down to about 0.5 and up to 1.5 and down to 0.5. So the ratio of the two is 1/2, or is 3 rather. So for this particular antenna connected this way, we would say the standing wave ratio is 3. But the thing to remember really is that it's just a way of measuring how good a job you're doing of transmitting energy from the feed line into the antenna. And that depends on various things. It depends on what kind of feed line connection you have here, but it also depends on your antenna and how well it's tuned to the frequency that you're trying to send from the radio. So to me, I think it would have been kind of clearer if people talked about sort of the ratio of the amplitude of the wave in the antenna to the wave in the feed line. But the convention that's been used in radio for a long time is to look at this standing wave ratio.